inviting me to this wonderful place here. This very old school, very famous school, and also to talk about these very interesting topics. And I'd like to take the perspective now from looking at materials with the eyes of a material scientist, but the materials that we find in biological systems. And I decided for today to take a very special perspective. As Yves said, we are all optimistic of learning a lot of things from nature, but I'd like to start with the perspective of Julian Allwood. So this is a very interesting book that this person from Cambridge wrote. And I learned about it by Julian Allwood starting out a materials conference saying that if you take the energy problem seriously, please stop developing materials. So that was an interesting start from a materials conference. And so the idea behind this argument was the following. Well, if you take a device such as this, for example, it contains an incredible number of different materials, metals, plastics, semiconductors, rare earths, all kinds of things. It takes a lot of energy to make this, and then basically it's highly dangerous waste, and it takes, again, a lot of energy to disassemble everything if you would like to reuse or recycle some of these materials. Now, if this was made out of one single material, we would just crush it and make it new. And I think this is something that I thought merits a second thought. And this is a little bit the theme that I would like to put in front of the talk. So it means that we could look at smaller temperatures, for example, to save energy, smaller amounts of materials to save energy, a smaller variety of materials to save energy in recycling, and of course a longer lifetime. And then this very, very naturally brings you, as you will see, to biology. Now, this is very similar to one of the slides that Yves has already shown. And you'll see the point I'll make with this. So this is just cross-sections of beams that are meant to provide bending rigidity. And basically, if I start here, if I take a square cross-section, I get a certain bending rigidity. Now, the same bending rigidity can be obtained with half the amount of material by just making this cross-section, a third of the amount of material with this cross-section, and a quarter of the amount of material with this cross-section. So that's one strategy. And of course, the other strategy is to do something to the chemistry to make the material stiffer. Again, you get a reduction in material just by preserving the shape or making it 3 times so stiff. You have another reduction of the amount of material. Now, basically, and you've said this, Yves, before, you have these two strategies. So on the vertical direction, we have chemistry. On the horizontal direction, we have geometry. And of course, we can combine both. That's, of course, a very good strategy for highly performant materials. But giving this a second thought, we can also now think about, in terms of the Allwood remark, that having too great a variety of materials might be how shall I say, a challenge for recycling and for energy on that side. I think it might be worth thinking about it that actually just by this geometric change, you get actually a much bigger reduction than by chemistry. So a factor 3 in Young's modulus, quite substantial. While, and you see that the material amount that you've saved is not nearly as much as what you can do by geometry. So I think maybe by including into our design strategies this consideration of sustainability, we might come to quite different solutions. I mean, this is a little bit the idea. Now, of course, natural systems are sustainable by nature, I would almost say, because of the resources being recycled for very natural reasons. And therefore now I'll move a little bit to how to look at nature. Now, the inspiration by nature is as old as humanity, and I'll show you a very simple example, in this case from Galileo Galilei, about geometric adaptation. So actually, this is the original drawing from his Two Sciences, where you see the typical shape of a bone for a large animal and the typical shape of a bone for a small animal, and you can see the different aspect ratio. And this made him discover the concept of strength, actually, which I think was not very well known before. So now, just let's make the argument. So here is an animal, scale it by a factor a. So I just increase all the dimensions by a. Then obviously, if I suppose that the force is mostly governed by the weight, the force that is going to act scales with the third power of a. While, of course, the area of that bone that will have to sustain the load scales only with the square of A. And this led to realize Galileo that if the force scales with A3 and the area scales with A square, then there must be a change in the shape to accommodate this. And so he recognized that strength was an inherent material parameter, and that, of course, since the strength was limiting the bone, you had to change the shape of the bones to adapt to big animals. Now, this is a very interesting discovery, of course, and a very interesting concept, too. And then if you go to the letters that Galileo wrote to his daughter, this is very nice. He was already an old man, and he just learned that a whale has stranded in Pisa. And, of course, he was living in... not living in Pisa, he's rushing despite his age to the seashore to verify whether the bone of the whale was actually like the bone of a big animal or like the bone of a small animal. And his theory was that it should be like the bone of a small animal because a whale was swimming and not walking. And what a disappointment, the bone of a whale is like the bone of a big animal and not like the bone of a small animal. And actually, the misunderstanding or the error that Galileo made is that it's not the weight that governs the force, it's actually the muscle strength. And of course, the big animal has bigger muscles and pulls more strongly. And therefore, there's a good reason for having bones. So I just learned from my colleagues in orthopedics that if you stumble, the stress you get on your hip is 10 times your body weight. You may just calculate how much that is, if you wish. It's quite substantial. So now, this is now the argument about architecture. So here the architecture was just a change in aspect ratio. Now I show some steel objects. I hope, Eve, you like this. Wool, cable, honeycomb, something made of steel sheets, and even some architecture. And of course, these have very different properties, though they are of a relatively similar material, all different types of steels. And the reason I'm showing this is that I would like to make the point that these structuring here is done at very different scales. So of course, the architecture is at the meter scale, while the wool is at the sub-millimeter scale, and so on. And what nature is very good at is, since this is a bottom-up growth, is to do this architecturing on many, many scales. And here's just one of those examples. So this is the skeleton of a glass sponge from the deep sea. And here you can see the arrangement of the glass fibers in horizontal, vertical, and diagonals, very much like in this architectural here. But then, just going down the scale, you realize that the glass fibers, they are not plain glass, so they are actually layered silica. Here are some of the silica layers. In between the silica layers is a tiny amount of organic matrix. And basically this is like armored glass, because the armored glass is a layered glass where if a crack propagates through one of the layers, it's stopped at the interface and will not crack the next layer. So this glass gets much better strength than normal plain glass. The only difference to typical man-made armored glass is that the glass layers are not millimeters, they are just 10 microns here. So you have many, many, many layers. And therefore, these glass fibers are hardly, almost unbreakable. Now, this just shows you that here you get a very special mechanical property out of microstructure. The question is mechanics the only thing to talk about? And the answer is, of course, no. And I just show you a few examples here. One example here from literature. This is just the colors of a butterfly wing, which is made out of a fairly boring chitin material that has no color at all. There is no special coloring molecules in there, no dyes or anything. And the color comes just from the periodic arrangement of these lamellae in the wing. So there's also, architectured materials, if they have the right length scale, can also, of course, manipulate light. Another example you carry around with yourself, this is the cornea of your eye. And so the cornea of your eye, very simply speaking, is a composite made of collagen fibrils, collagen fibers, so collagen, the same material you have in your bones and in your skin and in your tendons. And, well, very surprisingly, this tissue, as you know, of course, is transparent. So why is it transparent? Well, I give you very briefly the trick and then show you some pictures to demonstrate this. So these fibers here, of course, have a different refractive index than what is around the fibers, which is a very rich proteoglycan matrix, proteoglycan-rich matrix. So if you have a regular arrangement of fibers on an almost a lattice, then there is something that we call Bragg's law. This is light diffraction. And, well, this is a very simple equation, so I'll discuss it a little bit. So this is the spacing between the fibrils, essentially. This is the wavelength of light, and this is an integer, can be 0, 1, 2, so that's the orders of diffraction. And of course, the property of the sinus is that it has to be smaller than 1. So if I make sure that 2 times the distance between fibrils is smaller than the wavelengths, then the only solution to that equation is for n equals 0, and therefore theta equals 0, so there is no diffraction. So basically, in a regular grating, if the spacing between the diffracting elements is smaller, or 2 times this distance is smaller than the wavelengths, there cannot be diffraction. So that's the principle of an optical filter. And this is exactly what occurs, actually. So this is an electromicrograph in the cross-section of the cornea. And this is the electromicrograph cross-section of the sclera. So if you look your neighbors into the eyes, you'll realize that the sclera is white. Now, why is the sclera white and the cornea transparent, although it's made of the exact same chemical composition? It's just a ball. Well, the reason is that in the cornea, you have a regular arrangement of fibrils with a very small distance, and this is the very same scale what's going on in the sclera. It's much bigger. So the sclera diffracts light, while the cornea doesn't. So here is the typical range. So that's here 400 nanometers. And it turns out that 2D in the cornea is smaller, is about 150 nanometers. So it's just such that visible light is not diffracted. But of course, ultraviolet light is, which is not a disadvantage. Yeah? And of course, in the sclera, everything's diffracted. So just to give you the idea that you can also manipulate light. And I'm not going to talk much about this. These are actuators, because this is a topic that you're going to hear about tomorrow. These are all plant seeds and various plant actuators. And they are also based on the architecture of cellulose in the plant cell wall. And since this is going to be a topic tomorrow, I can just leave it at that. So that was a little bit my introduction to what I'm going to say now, because I want to come back to this now and say, well, our architecture, geometric arrangement can generate a broad range of properties, mechanical properties, optical properties, even active mechanical behavior. Now, how much can we use this in order to look a little more into the direction of longer lifetimes, smaller variety of materials, and so on. And basically, let's just go on by saying what I will now try to do is to show you some examples in particular on how to increase the durability of materials. So this is my last point here. Of course, a longer lifetime is also a way of saving energy. And how can we increase the durability of materials? Mostly by geometry. Now, here are three things. So I'm sure that Mason, who is of course in the audience, will recognize this picture. I'll say just a few words about this. I'll say something about generally about the mechanics of tessellation in a sort of general concept, how this is going to affect the lifetime and the properties. I'll talk about pseudoelastic proteins and interesting properties that some proteins may acquire that also dramatically increase the lifetime. And finally, I'll talk about maintenance and adaptation, which of course is also a way of increasing lifetime with the example of bone. So I'll try to cover this a little bit with a few examples. And well, if you want to read this, as you see, Yves is quoted on some of this. These are some viewpoint articles on these kind of topics. So let me start with the first thing that I want to cover. These are pseudoelastic proteins. Now, so this is primarily work of the group of Matthew Harrington in our lab in Potsdam. And here are two interesting protein-based materials. So one material is the major constituents of these fibers here that mussels, moules, use to fix themselves, to anchor themselves onto rocks in wave-swept habitats. So they are getting very challenged by waves, and therefore they need to anchor themselves onto the rocks. And you can imagine that these fibers, on the one hand, need to be stiff to anchor the mussel to the rock, but in case a very strong wave comes along, it would be very clever to have a material that is also able to dissipate a lot of energy without having the mussel actually being swept away. So I think it's very important to have a very durable and very interesting properties for these fibers. Now the other example is these egg case here. So these creatures here, these whelks, they put their eyes into cases of that nature. And again, this is a protein case, and these egg cases just swim around in the ocean. And of course, they don't want to be eaten by whatever swims around in the ocean. So they are made so tough that nobody wants to eat this. Yeah, this is exactly the way you don't want your steak. And therefore, so the question is, how do you make a protein so incredibly resistant to fracture? And the stress-strain curve of these materials are shown below. This is the load that's applied, and this is the strain. And you see these things have cycles. Well, let's look at this material, for example. It's fairly stiff if you start to bite on it. If you bite sufficiently strongly, it starts to deform like crazy, but it doesn't break. It deforms 50, 80%. So your steak, you bite in it, it deforms, it doesn't break. You stop biting, and it just comes back, and then you bite again and again and again, and it just doesn't break. This one has a slightly different behavior. This is now that fiber that is being stretched. So again, it's very stiff in the beginning, so the muscle holds to the rock until a certain point where the muscle really is teared away from the rock. And again, you have a very large deformation, means that a lot of energy can be released, the muscle can move away. But interestingly, again, the fiber is not broken. And when it comes back, you see now it has changed properties. It's not like here, it's not a cycle that immediately goes back. If you wait some time, a small amount of time, it goes back around this curve. So now the material is much less, has a much worse property than it had before. In particular, the stiffness in the beginning is gone. But if you wait a day, it's back to the original. So the question is, what are the designs for materials such as this? And because this, of course, is a design for durability. Okay, so I said all this. Now here, just to give you sort of a little background on these things. So these fibers are, as I said, made of proteins. The major part of this filament is a protein and has a collagen-like domain and some flanking domains that can unfold, which I call here the extensible domain, and here is another one. And this is what builds the fiber. So just to give you, I don't go into details, I just give you the idea of what's going on, roughly speaking. So here is the connector, this is the collagen, here is the deformable region, here is another connector, and now we're going to pull. Here is the stress strain curve, stiff in the beginning, large deformation. So in the beginning you start to pull on these folded domains here. The connector doesn't deform very much, it's just a very stiff connector, but this thing here changes, and you see now it starts to unfold. And what these little red connectors, these little red bonds are, these are zinc histidine bonds. So histidine is an amino acid that is able to be cross-linked to an other amino acid by a metallic ion, which in this case is zinc. So this zinc cross-links these little bonds here, and on unfolding, of course, the covalent chain that goes from one end to the other is still holding. You have broken all these red bonds, but you haven't broken the connection between the two ends, and therefore, so this is what some people call sacrificial bonds. And on the way back, the sacrificial bonds are still broken. So now if the whole thing folds back, it has a very, very small modulus, because now it's just the unfolding of the protein that holds back. So it has lost its properties. But of course, if you wait an hour or if you wait 24 hours, what's going on is that these red bonds, since it's just a zinc ion that cross-links these two, the zinc ions finds again its histidines and it cross-links the whole system again, and then we can start all over. So every 24 hours there can be a very, very strong wave during the tide that tears the muscle away, and it can recover again within 24 hours, roughly speaking, to get back. And I think this is just, I don't go into any details, this is just as much as we know about these arrangements. It's a very, very complex three-dimensional arrangements of the proteins to allow these sacrificial bonds actually to work properly. So the geometric arrangement is almost a protein crystal. So the geometric arrangement is really very, very important to make this system work. Now a few comments about the other system. Now, how do you make something that's unchewable? So this is the properties. Now this is very interesting. Eve talked about phase change materials. So here is a phase change material. This is diffraction at 0% strain, diffraction at 40% strain. We just integrate this so they can see it better. So this is the red, this is the green. Not only did the peaks shift, so means that the protein is being stretched, but actually the completely different peaks have appeared. So somehow this protein underwent a phase transformation. And basically here is what's going on. This protein at very small strains is in an alpha helical conformation. And an alpha helix is a conformation where hydrogen bonds hold the alpha helix in multiple places together. So there are many hydrogen bonds that hold this helix together. And in fact, there are many segments of these molecules in a row. So here's an alpha helix, the next. So everything's alpha helical here in the beginning. When we reach the point B, you see that, well, this was rather stiff. So all these alpha helices have just extended a bit. So all the hydrogen bonds are still holding, but you have stretched many of those. So there's a little stretch, and of course the strain that's associated with this is very tiny until we reach the point B. And then something happens, a phase transformation occurs, and this phase transformation is actually a transformation from an alpha helix to an extended conformation of that molecule. And that goes into this is a sudden transformation. But of course, if the sudden transformation happens only in one of those four, there's a little bit of elongation. If you then transform another one, there is more, and then until you reach the point F, all the segments of that molecule have transformed into the extended conformation. So this is completely analogous, by the way, to what's going on in nickel-titanium fibers that you use to move your teeth around, where actually on stretching, you're changing one phase to another phase that has a bigger lattice spacing, and that allows what people call superelastic behavior. And actually, the nickel-titanium model works perfectly for these proteins. So here are two examples of how to use just proteins. Well, I'm not saying they're of course different proteins, but it's at the end it's just protein, and how an arrangement with microstructure allows you to make very fracture damage resistant material. This is just a historical remark, is that these fibers, these muscle fibers actually, not the ones of the usual muscles, but the ones made by these huge shells here, namely pinna nobilis, they were actually used as for textiles. Not ordinary textiles, but very, very expensive textiles. And these fibers here from that pinna nobilis, I mean, this muscle, this shell, sorry, is growing in near Sicily in the Mediterranean, and it was used until in the antiquity, in the Middle Ages, and was called mussel silk. And these pictures here from an exhibition that was like 10 years ago in Switzerland by Felicitas Meda, and these are gloves for the Pope. You see the kind of usage that these fibers got, and this is a tissue that was made. And interestingly enough, again for the history, this tissue has no dyes at all, so it has not been painted, and supposedly this is the face of the person that was wrapped in the fiber. It's not known. I don't know if this is just I don't know, some small history, or whether this is really true. But the idea was that these special fibers, they would actually directly copy the picture that was there, and it's not completely impossible, because actually, since this is containing zinc, and you have these zinc histidine bonds, there could be a chemical change, and actually that could happen. But as I said, there's no proof there, and I didn't go there to verify. So, but it's an interesting story, even if it's not true. Now, let me go back. So this is the pinna nobilis. Let me go back quickly to the byssus of the muscle, because the pinna nobilis is again anchored by these fibers in the ground, but it lives in fairly quiet sea, while the byssus lives in very, very rough seashores. And so not only does this fiber require interesting properties for the fiber itself, it also requires to be protected against wear. Now, this is the challenge to the engineers in the audience. How do you design a wear-resistant coating for a fiber that has to extend by 100%? This is the challenge that I'm posing to the engineers here. Well, here is the solution found by the muscle. You look. So this, never mind these pictures here. This is Raman spectroscopy. This is confocal Raman imaging. And you see these bright spots here that look like precipitates. Well, they actually are precipitates, but not of another material. This is just the cross-link density. And now the cross-links are just another version of metal coordination bonds, namely these bonds here. This is not zinc now, this is iron that coordinates these dopa catechol, like these dopa side chains of amino acids, and creates these very, very hard droplets. So they are much harder than the matrix surrounding them. It's the same protein. The dark yellow is the same protein as the light yellow. The only difference is the different cross-link densities, as schematically shown here. And now here is the trick. The trick is you have to design a material that is soft in tension but hard in compression. Now, why is this hard in compression? Well, if I have lots of little balls here and I push on them, well, one ball hits the other ball, so this is pretty hard. However, if this goes in tension, the ball is hardly deformed. What deforms is the matrix in between the balls. And therefore, here's an extensible material that's hard in compression and therefore suitable as a wear-resistant coating for an extensible fiber. Now, this is just, this is work from Yael Politi in the lab, and this is just to make the point that these metal coordination bonds are really very interesting strategies. In fact, it turns out that just by cross-linking, you can make a protein harder than bone, and just by these cross-links. And one example is here. This is a spider, and this is just the device that the spider uses to inject the venom. It's made of chitin, and the prey has a carapace made of chitin. So how do you make chitin harder than chitin? Well, the trick is you don't use chitin, you put actually protein in the tip, and the tip of this chitin needle is actually made of protein. And what you see here in this micro CT is the distribution of zinc. It's again the zinc histidine that I was talking about earlier. And in fact, the zinc cross-linked protein is harder than the chitin, and that's actually the hard tip of that injection needle that is actually penetrating then the chitin carapace of the insect or the other arthropod that this spider is eating. So now back, this was just a small remark, and so these spheres are also very hard. So this is now sort of the same picture as before, just to emphasize another very interesting aspect of this material. Namely, here is a hard material, namely this dark yellow material, but actually the feature that made the trick is that these hard particles are not connected to each other by hard bridges, but by a soft material in between. So actually the trick here was to take the hard material and separate it into pieces, and even though it's separated in pieces, if you use it in compression, the pieces touch each other and it is as hard as almost as hard as a continuous hard phase. So making things into pieces is an interesting thing, and this is the concept that I'm going to talk now, which is the concept of tessellation, which is another very, very common principle in natural systems. And I mean, I don't know if Mason is going to talk about this, perhaps. In any case, I'll just mention this very briefly. Tessellation means take a hard component, another hard component, and a very thin, either nothing or a very thin layer in between. Then clearly this small volume here has a very large effect, because in compression it's going to be hard, but if you put tension on this soft green phase will actually take the tensile load. So this is a principle that you can see. So this is work with Ron Schacher, who is also here. This is the shell of the turtle. Now, that's something I had to learn as a material scientist, is actually that the shell of the turtle is nothing else than bone. It's the thoracic cage that's being transformed into a carapace. So basically, by taking a cross-section through this turtle shell here, you see the ribs. So here's one of the ribs. So normally if I take my ribs and I would cut them, then I would see individual ribs surrounded by soft tissue. Now here's the rib of that carapace, and you see it actually joins up with the next rib that's coming here through this suture. But now, if I take, so this picture here is showing in bright, it's showing the mineralized bony phase, and in black is soft tissue. Now, this is like playing a maze, yeah? Now I'm taking this arrow and I'm trying not to cross any white. So I can go here, 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 here. Oh, I went through it. So these two ribs are joined, but they are not physically joined. There is no bony bridge from one rib to the other. Now, taking now a section through this part of the suture, this is what it looks like. So it's a fingering, it's interdigitated in 3D in a very, very complex way, but you can see that none of the mineralized phase is touching the mineralized phase of the other side of the rib. So it's interdigitated but not connected. So what's the point of interdigitating without connecting? This is the simplified model of it. Just take the model of my fingers. If I'm putting a soft matrix between my fingers, you see that at small deformation, this is very soft. While at larger deformation, this now starts, these fingers start to bump into each other. It's getting very stiff. So this is the measured behavior of bone, the measured behavior of bone with a suture. And you see that for a while, almost no load happens on bending, and only later this starts when the fingers start to bump into each other. So this is a design for a carapace that behaves very soft when you do small deformations such as breathing, walking, swimming, but behaves very hard for large deformations if somebody bites on you. So here is another trick on how to use tessellation. So this is now a Mason's example. Just very, very briefly, these tesserae. So, well, I find it amazing that creatures such as sharks have skeletons actually made of cartilage. Now, the properties of cartilage you can test yourself. Yeah, this is this. Yeah. So the white shark comes along with his big teeth and then has a jaw made of this. You don't believe it, right? Well, there's something that helps, these are tessellations on the surface of this cartilage that Mason is very interested in, and another one of his pictures where you can see a large view of many of those mineralized tiles. Now, just imagine, take a rope of cartilage and put ceramics on top. You wouldn't like to do this because as soon as you bend this, the ceramics will just break and everything is gone. But instead of ceramics, you do what you do in your bathroom. You put tiles. Then you can actually bend, and then the same thing happens as with the extensive abrasive-resistant coating, is that when you're bending on the tensile side, what you're stretching is the soft material in between the tiles, and when you're compressing on the compressive side, the hard tiles bump into each other, and this is what gives you rigidity. So I think the tessellation is absolutely essential in these bones. So this is mineralized, so these tesserae are mineralized cartilage on the surface of cartilage. So here's the cartoon, Mason's cartoon about this. On the compression side and on the tension side, what's going on. So, of course, I had to show another picture of Yuri's because now this leads very, very naturally to the concept of these interlocked materials that Eve already introduced. And here's one that I like, just made of tetraeders. So put two tetraeders side by side, add another one like this, add another one on top, then slide them in from the side, and so on. This makes a material that is stiff in bending just because the elements in 3 dimensions lock each other. So if you put nothing, all you need to do is to squeeze them together by some load from outside, or instead of putting nothing, you can also have some glue, some resin sort of impregnating this, and then you have a soft tissue connecting the hard elements. What I find really interesting is that you can actually remove one of the elements and it still holds together. That's what Yuri Esrin is showing here in this panel here. So there are lots of interesting concepts that actually, as you can see, can be translated into technological ideas. So let me just push this a little further and go back to some of these glass sponges. So you remember the glass sponge that I showed in the very beginning, where the inherent brittleness of glass is reduced by the fact that the glass is separated into individual lamellae. So for those who are not material scientists here, you all know that the way to break glass, you make a scratch and then you just bend and the crack will propagate. But of course, if you have now glass layers of 10 microns glued to each other, you make a scratch, you bend, and the crack will propagate 10 microns, and then it will have to be nucleated again. So it's obvious that just by subdividing into many, many lamellae, you are dramatically improving or reducing the inherent brittleness of glass. And I mean, this here is an example of such a glass sponge where all the dark lines here are just glue layers in between glass layers. And here are some examples, for example, of how crack propagates in a plain glass, biological glass, or for example in this multi-layered glass where you see that the cracks don't propagate but stay where you have actually damaged the material. Now this is a very, very simple-minded concept. So this is the telephone book concept. I know the younger people here don't even know what telephone books are because now it's all on the web. But in former times, we used books that were thick like this with many, many pages, right? And then just try to think about the difference in the mechanical behavior of a telephone book intention versus a plain piece of paper, yeah? Well, instead of paper, we can, for example, take aluminum sheets. That's one of my colleagues in Leoben has done recently, and he's shown that indeed you get a dramatic increase in strength. So here is the plain material. If you put a crack in this plain material, there's one problem with this that everybody in material science knows, is that when you now pull on this, then you get an increase of the stress at these tips here, which is actually given by this equation, where the increase in stress at the tip goes with the square root of the size of this crack. And that's a problem because, of course, if the stress here is larger than what you're applying, then indeed this will actually make the crack propagate. And then you get this very nasty behavior that when the crack just grows, the strength is actually coming down. So that's for a completely brittle material such as a ceramic. Now to take this brittle material and now subdivide it into individual sheets, and now I'm putting the exact same length as a crack, just that this now cracks 1, 2, 3, 4, how many? 4 of those sheets. Now actually the only thing that you did by now, if this was a telephone book, you have removed 4 pages of your book, and if you had 1,000 pages, now you have just 996 pages. It's still good, yeah? And actually the strength just decreases like this. It's a dramatic improvement in the properties just by going from a plain thing to a multi-layer thing. And this can be generalized to materials that have periodically varying stiffness, and such as, for example, in these glass multi-layers or any other multi-layers. Turns out you need a minimum contrast, like 5 or so, to really get a good effect. But with a contrast of 5 in terms of elastic modulus between the layers and the layers in between, you get a very, very strong reduction in the driving force of cracks across this multi-layer. So that's explained in these papers here. So separating materials into pieces is dramatically reducing the fragility. Now let me talk about something that I call here pseudo-elasticity, pseudo-plasticity. Now plasticity is known in metals, and in metals plasticity, which is permanent deformation of metals, comes from the fact that your periodic arrangement of atomic layers is interrupted by a defect, and then you're propagating the defect rather than by changing the chemical bonds. Now, how do you translate a concept such as this into a composite material made only of polymers? Now, here is the scheme of a tendon. Not only the turkeys do have these great tendon structures, we also do. And mice and most animals who have tendons, these tendons are multi-scale. And so this is a multi-scale rope. And now what you can do, or what we did, in fact, is to use some special physical techniques based on X-ray diffraction at the synchrotron to measure simultaneously the elongation of molecules and fibers and the complete tendon as a function of load. Okay, well, this is the method. I'm not going into details. I'll just give you the result. So now you're stretching your tendon until it almost breaks. And then what we measure in this tendon is that the molecule, which is a triple helical protein, collagen, that this molecule has stretched 1%, that the fibril, which is an assembly of these triple helices, has stretched 2.4%, while the tendon, which is the assembly of everything, has stretched 15%. So how do you make a fiber where the complete system stretches 15%, the subcomponent stretches only 2.5%, and the subcomponent of the subcomponent only 1%? That sounds strange. Well, the explanation is very simple. Well, you forget, I always need my hands for this to explain. So elongating the sum of my two hands will make me cry, but if I do this, I can easily elongate the sum of my two hands without any pain. And this means that shear between the fibers is the clue to this. So here is another very interesting effect of subdividing materials into a tessellation, because now the surface between the tesserae, or in this case the fibers, allows you shear and therefore a much larger deformation than the individual fiber. This is actually a fantastic way of tuning the stress-strain curve of a macroscopic material by just changing these, adapting these values by the right materials here, down here, the crosslinks and so on. So you can actually design the shape of a stress-strain curve in this way. So the same thing also exists in bone. So this is just an image of bone, which is also consisting of these collagen fibrils. The only difference to the tendon is that it's now reinforced with mineral particles. And doing the same study on bone, you find that the same is true, that actually bone is able to deform twice as much as the mineralized collagen fibrils. And the reason is that the interface between these blocks provide the deformation. In this case, this interface here is made of phosphorylated non-collagenous proteins and also some mineral in it and so on, but not as much as on the surface of the collagen. So here are two materials that do this. How universal is this? So you've already, Eve also mentioned wood. By the way, here is your speaker, yeah? Fairly tiny compared to this, right? Now, how do you make a material as good as this? Well, I think I need to show this because this is about the holes in material space. I have to spend a minute on this, although it's a little out of the point that I will make later, but still. So if you want to build the highest column with the lowest amount of material, this is what you need to maximize. And here is an Ashby map actually collected, I think, by Mike Ashby in a very early paper already, with all kinds of materials, engineering alloys. And here is wood in the direction of the fiber. Well, perpendicular to the fiber is not important because it's not used that way in nature. And now this is a log scale, and this is the line that has constant values of the parameters that I'm interested in. I'm now increasing this interesting parameter. And you see that, well, well, wood is better than anything, at least for this parameter. And this is because the density in wood is so low, and the density in wood is low. You know that wood is floating in water. The density is low because it has the lumen in the center. It has this, it's made of this cylindrical cells. So, but even though the density is low, it still needs a decent modulus. And now let's talk a little bit about the modulus, and then also talk about plastic deformation of wood. I don't know, if you buy your very expensive Rolls-Royce car, yeah? So then you have this wooden, made of real wood, these wooden frames in front of your car, which of course implies that you have to be able to do plastic deformation of wood. There are several mechanisms for that, but here is one. So these wood cells are made of, are tubes essentially, with stiff cellulose fibrils running at a certain angle around the lumen of the cell. And if you're pulling this cell, and again here is a synchrotron experiment that is able to measure this angle, if you're pulling the cell, this piece of wood in this direction, what you see is that the spiral angle, which is called microfibril angle, is actually decreasing. It goes from 45 to 35 for an elongation of 15%. So I need my arms again. This is a cellulose fibril, this is another cellulose fibril, and now changing the angle. See what's going on? It's shear between the fibrils. And this allows plastic deformation. Why does it? Because cellulose fibrils are built in this way. Here is the component, the tessera, the individual stiff component. This is the matrix that surrounds it, but this matrix that surrounds it is in large fraction hemicellulose that has 1/2 of the molecule almost identical to cellulose and is integrated into the fiber. The other part is branched and sticking out. Here is another fiber that has the same principle. And then lots of weak bonds that connect these fibers in between the two stiff components. And of course, if you're able to break some of these bonds and then to reform them in a slightly different position, you have achieved a plastic deformation. And again, like in metals, it was a localized deformation. It's a different physics, of course, it's no dislocation, but the general concept is the same because, again, the deformation is completely localized. And so people are now, I'm just showing this from our friends in Finland in this case, people are now developing materials based on these ideas and by connecting stiff elements with multivalent polymers in between them and so on. So, sorry for the German in that slide. But once in a while we write reviews even in German. And so this is just summarizing these pictures. These two pictures are just summarizing two of the principles that I showed you before with these fibers and the interfaces between them. So this is the plasticity concept. So here is a fiber that has binding sites with the other fiber, and I'm now shifting one blue fiber against the other blue fiber, and you see that these bonds A and B now are dangling, but instead we have bonds C, D, E, F, G that are connected, and if I count here, I have 5 bonds connected, here I have 4 bonds connected. This is as strong as this, but it has been permanently deformed. So this is what I mean with localized deformation in the interface. This is the other example that I showed earlier with the muscle that is attached to the rock. Here the bonds now are connecting loops of the same molecule. If you unfold it, the molecule stays intact, and it can refold and reform. So this is reversible. So this is reversible. Some people call this self-healing. This is irreversible. You can call it plasticity if you wish. I skipped this because of time. And I'll finish with a last comment about adaptation and maintenance. talking about a little bit more about bone. So basically, bone has, in our body, has a very interesting ability, namely to renew itself permanently. So approximately every 5 to 7 years or so, you have a new skeleton, completely new. And the interesting thing is that this renewal is not completely random. Actually, I'll show the next slide first. I'll show you this first. So these are the actors during that renewal. In this histological slide, this up here, that's a little pink, this is mineralized bone. This is newly formed bone matrix. It has a different color because it doesn't have mineral yet. This is going into it later. These are cells called osteoblasts. Let me put some arrows. They are adding new material, and you see they're sitting here in this row. They're synthesizing collagen, putting it down here and making this matrix. Some of these cells stay behind. They differentiate to osteocytes and stay within the bone. This is an osteoclast that actually removes bone. It eats it away. It's actually very difficult to eat away bone because the mineral needs very acidic environments that's made by these cells. So you realize that you have actors removing, actors adding, and you have a sensory system here. So this is a classical actuator sensor system embedded in a material that renews constantly. And that's why I call this an adaptation and maintenance cycle, because this set of cells actually renew the bone constantly, and actually they do so by removing bone primarily where the bone is weakened, either by damage or because there is a specific unusual load coming along. So this cycle replaces damaged material, thus preventing fatigue. So this is a way of avoiding fatigue, is to just remove damaged spots. It also allows to adapt to the loading situation. I'll say a word about this. And this is less important here, but very important for us as creatures. It mobilizes and stores calcium and phosphate because this is our main storage for these ions. Okay, you've seen this. Now, here is just the example of what this controlled remodeling is actually doing. This is just a human vertebra as a function of age in a fetus immediately after birth and in an adult. Black is bone, white is bone marrow, and it's a cross-section approximately around here through one of the vertebrae. Now, look at this. So now, in terms of engineering, you find immediately that this makes sense because you have struts vertical and horizontal. Actually, the loads are uniaxial, essentially. So vertical struts are good to sustain the vertical uniaxial load, and actually the horizontal struts are there to prevent buckling of the vertical direction. That's at least what people say. By the way, this changes a lot with osteoporosis. I'm not going to talk about this, but just as a small remark, in osteoporosis, primarily the horizontal struts go away because they are less critical than the vertical ones for the type of loading that we put. But interestingly enough, in the fetus, this arrangement is not vertical horizontal. It's central. It's radial. It goes from a center outwards, as you can see. So it's a completely different topology. And if you just look at what's happening at birth, you still have some remains of that central arrangement, but it's remodeled into vertical horizontal. I didn't discover this, obviously. This is known since 150 years. And I think I like to show this slide because that's a very early collaboration between an engineer and an anatomist. So von Meyer-Kuhlmann, a Swiss engineer, building bridges, and recognizing the fact that the arrangement of these trabeculae are actually following the stress directions. Julius Wolf, an anatomist in Berlin at the Charité, he discovered the same thing. Plus, what he also noticed that if there was a fracture in a piece of bone, and the fracture healed badly, means with the bones not put in the right place, you will get a rearrangement of the architecture that would actually adapt to this abnormal situation. So even though the situation was abnormal, the bone would remodel in such a way that it would cope best possible with this abnormal situation. And these are some of the original drawings of what happened in these particular fracture cases from the 1870 book. So in terms of materials, this adaptation and maintenance cycle is basically small-scale recycling, really. Now, just a word about what really healing is, bone healing. This is not small-scale recycling, this is large-scale recycling, because now the body really synthesizes bone where there is normally no bone in the form of a callus here. This is what thickens the bone for a while until the fracture is healed, when this callus is being removed again through this normal adaptation and maintenance cycle. So I'm just mentioning that this is a complex process where bad material is deposited first, good material is added on top of the bad material, and at the end everything is removed. It's a very complex, intricate process that looks like bricolage, more or less, yeah? Really. So I'm concluding here and showing you again these 3 boxes that we had before. So basically, these examples here of the tessellations, this is really damage resistance. These are material that are designed in such a way that's very difficult to damage them. You can chew on them, they never break. You can, tessellation is a very, very typical example. Then some materials are designed for damage tolerance. So even though they have lots of cracks, they still function. Finally, when I talk about maintenance and repair, this is really recycling at the small scale, continuous recycling at the small scale, and large scale recycling later. So you see there are lots of strategies around to make materials more durable. I think probably a lot of this can be translated into engineering, although I'm not optimistic to the point that I think that any of this can be translated directly. It's at best inspiration, I hope. It's not solutions for us. And the reason is very simple. If you find a solution that is supposed to optimize a certain problem, you have to take boundary conditions into account. And obviously the boundary conditions of nature are very different to the boundary conditions of the engineer. Prices, availability of materials, synthesis, and so on and so on. So it would be very surprising if any of these natural systems could be translated directly. But I think at least the strategies are being worth looked into. Thank you.